Hello, in this video we'll learn about Ampere's law. This law is applied on a closed path. This path can be real or imaginary. This path is called Amperian path. In short, we write AP for that. And the mathematical formula for Ampere's law is this. Integration of B dot dl is mu naught into summation of I in. Okay. We have to take one direction as circulation direction. Circulation direction means the direction in which we have to circulate along this path. So imagine you are moving along this path from one point to the same point again along the whole cycle. So you can circulate either in this direction, so that is anti-clockwise direction, or in opposite direction, that is clockwise direction. So that is called circulation direction. So while circulating or while traversing along this path, you have to mentally divide this Amperian path into many small parts. And suppose we name them as dl1, dl2, dl3, dl4. These are vectors, in fact. dl1 vector, dl2 vector. If someone sees from inside of this Amperian path, all these dl vectors will go along anti-clockwise direction. Now we have to find b dot dl on every small part. So suppose the magnetic field at this position is b1. So this magnetic field is due to all currents which can produce magnetic field at this position. So B1 is the resultant of all those magnetic fields, and we have to find dot product of B1 and DL1. So suppose the angle between them is theta 1, so the dot product will be B1 DL1 cos theta 1. Similarly, suppose magnetic field at the position of DL2 vector is B2 vector, and then the dot product will be B2 DL2 cos theta 2, and this we have to do all along the path, and we have to sum all the B dot dls. This summation is nothing but integration of B dot dl. And this small circle means this we have to do all along the cycle, along the complete path. Okay, the Ampere's law states this. Integration of B dot dl along the closed path is equal to mu 0 into summation of inside currents. Suppose there are many currents. We are taking suppose I1, I2 and I3. I1 and I2 are inside currents because these currents are passing from inside of this Amperian path. And I3 is outside current. I1, I2 are to be taken with their signs. And how to decide their signs? The circulation direction we have assumed as anti-clockwise. Now place your right hand fingers along this direction. Thumb will point outward. So outward is positive. So whichever current is coming outward will be taken as positive, and the opposite current will be taken as negative. So here I1 will be taken as positive and I2 as negative. And note that B, the magnetic field at all positions like B1, B2, B3, etc. These magnetic fields are due to all currents. B2 is magnetic field due to I1, I2, I3, due to all currents at this position. Similarly, we had B1 here, so B1 is due to all currents. So here magnetic field means resultant magnetic field due to all currents, and here summation of In means only those currents which are passing through this Amperian path from inside of it. Okay, so this is Ampere's law. And to have some insight of what Ampere's law is, consider a straight infinitely long wire carrying a current I, and we know its magnetic field lines are circular lines like this, and we take an Amperian path like this. This is Amperian path. Suppose we take a small part dl as shown here. This dl is making an angle d theta at the position of current. And now suppose we have to find B dot dl, and the magnetic field is at this position is along the tangent drawn on this B line. So it is shown in this green. So this is magnetic field at this position. So this is the position of magnetic field here, and this is dl, and the angle between these two is suppose theta. So we have to find B dot dl, that is B dl cos theta. This is direction of B, this is the direction of dl, and we have to find the component of this dl along this B. So that is if we drop perpendicular from this tip onto this B line, so this perpendicular will fall somewhere here. Similarly, from tip will fall somewhere here. So the component of dl along B is this much. So this is dl cos theta. If the whole diagram is put back, so this pink line will be here, and this dl cos theta will be nothing but r into d theta. This is approximately equal to arc. So arc is radius into angle. So I can write dl cos theta as r d theta. And so b dot dl will be the value of b mu naught I over 2 pi r into dl cos theta. And dl cos theta is r d theta. So r will get cancelled. So B dot dl is mu naught I over 2 pi into d theta. So r is no more in this expression. And what it means is this, that any part, if you imagine any other Amperian path, suppose we take Amperian path, some other Amperian path like this. So even for this dl, we'll have the same B dot dl. If we have some other Amperian path, so between these two lines, B dot dl for this element will also be the same quantity, mu naught I over 2 pi into d theta. This we just saw that B dot dl1 will be equal to this much. So if we have another dl2, so B dot dl for this dl2 element will similarly be mu naught I over 2 pi into d theta 2, where d theta 2 is the angle which dl2 is subtending on this wire, and so on. So if we go on finding B dot dl for various elements, and if we add all these, so that is integration of B dot dl, so it will be equal to mu naught I over 2 pi, this we can take as common, d theta 1 plus d theta 2 plus and so on. All these d theta when added will surround this current and will become 2 pi, and then 2 pi will get cancelled, will be equal to mu naught I. So we can see that integration of B dot dl is mu naught into I, where I is the current which is going through this path, and it is an inside current. And if you circulate along this dl direction, if you move along this dl direction, you're moving in anti-clockwise direction, and if you put your right hand fingers along anti-clockwise direction, the thumb will point outward, and this current is outward, and therefore this is a positive current. So you can see that Ampere's law is being satisfied. Suppose current is inward, so its magnetic field will be in opposite direction like this. And here again, if you want to find B dot dl, and suppose this angle is theta 1, so the angle between B and dl1 will be now 180 minus theta 1. So B dot dl will be B dl1 cos 180 minus theta 1, and this will be minus B dl1 cos theta 1, and dl1 cos theta 1 is again r d theta 1. So it is a negative quantity. We have this result, and if you add all such results for dl1, dl2, dl3, etc., so that will give us integration of B dot dl, and then all d theta when added will become 2 pi. 2 pi will get cancelled, and we'll have a minus sign. So here we are getting minus sign because we are traversing in anti-clockwise direction. Outward should be positive, and the current is inward, and it's a negative current, so therefore we are having a minus sign here. So again, it's verifying the Ampere's law. If we have Ampere's path like this, and then we draw two lines, then we can see that the B lines for this outward current will be like this. These are B lines, and the magnetic field at this position is almost along dl, while the magnetic field at this position is almost opposite to dl. So at one part B dot dl is positive, while on another part B dot dl is negative. In magnitude they are same, so the B dot for this part is mu naught I over 2 pi into d theta, and for this part also it is of the same magnitude but with a minus sign. And if we add B dot dl of these two parts, they'll cancel out and become 0. Similarly, for these two parts B dot dl will also get cancelled for this part and this part, and so on. And we can say that total B dot dl will be 0. So it's becoming 0 because this current is outside current. So from this example we see that for outside current, obviously we are having B dot dl on every part. We are having B dot dl. It's not 0, but the integration of B dot dl is 0, because for some parts B dot dl is positive, while some parts B dot dl is negative. So if we add all these B dot dls, it will be 0. So whenever the current is going from outside of this Ampere's path, B dot dl integral will be 0. Now, having seen the contribution of three types of currents, one going outward from inside the Ampere's path, one going inward from inside the Ampere's path, and one outside current. So suppose I1, again I am taking I1 as outside current and its magnetic field is B, and the integral of B dot dl over the whole Ampere's path will be mu naught I1, and this I1 will come with positive sign because according to the direction of dl it is in positive direction. Now suppose we take another current, that is I2, and this I2 is causing a magnetic field as shown in red. So red magnetic field is the magnetic field caused by current I2, and since it is an inward current, then integral of B dot dl over the whole Ampere's path will be minus mu naught I2, minus because again as per the direction of circulation. Outward is plus, so inward going current is minus. And suppose we take another current that is shown in green, though it's hardly seen here. This is a current I3, and suppose it's causing a green magnetic field B, and the integration of B dot dl over the whole path would be 0 because this is an outside current. Now suppose all currents are present at the same time, I1, I2 and I3, so all will produce their magnetic field individually, and the resultant magnetic field is B resultant. So B resultant dot dl, the integral of that, it will be equal to, B resultant can be written as the summation of vector summation of B, B and B. This black B means B caused by current I1, red B means B caused by I2, and green one is due to I3. So dot dl, and then we can separate these integrals, and we have seen that integral B dot dl is mu naught I1, integral B dot dl with red B is mu naught I2 with a minus sign, and the integral of B dot dl, that is green B caused by I3, is 0. So this results into mu naught I1 minus I2. So this is what we have in Ampere's law. So only inside going currents come into this expression. Okay.